you very much, and thank you very much for the invitation. It's a pleasure to be here. Today I want to report on a joint work with Alberto Vezzani, which can be seen in some sense as an application of what he told us yesterday to the study of p-adic cohomology theories. So I hope this talk will illustrate how we can appreciate the properties of motives in this context. So we will be in this talk, K will be a perfect field of characteristic P. And we will be interested in varieties over K. To help to understand them better, we look for certain invariants, in particular cohomology theories. With certain nice or reasonable properties. And because of their role in the context of the Weyl conjecture, we often call them Weyl cohomologies. In characteristic 0, such a cohomology is provided by the Ram cohomology. So but in positive characteristic, the Ram cohomology does not work well. So let's look, for example, just at the affine line. So here we can consider one form such as x and p minus 1 dx, and they cannot be integrated. So this would give us infinite cohomology groups. A natural way to try to remedy this is to lift our varieties to positive characteristic, to characteristic 0. So we will take a complete discrete evaluation ring, V, with residue field K of mixed characteristic. And to simplify, we just will take the ring of weight vectors. And we will denote K as the fraction field of WK. So we want to lift to WK. Of course, the problem is that in general a global lift does not exist, and even if it exists, it's not necessarily independent of choices. The latter problem was addressed by Grothendieck, who realized that to remedy this, we should complete with respect to the p-adic topology. So let's go back to our example, and we will see that this still gives us problems concerning integration. So we had our affine line Kx. We lift it to W Kx, and then we complete p-adically. So we get power series which complete converge p-adically. So here in this ring we will find things like this. So this converges p-adically, and for each n, each of the summons, if we regard this one, the one form Pn x Pn minus 1 dx, is exact. But if we look at this one form, this is of course not exact because the p-adic convergence is lost by an integration. So at the end of the 1960s, Monsky and Weschnitzer came up with a solution for this. They said we should consider an additional growth condition. And they introduced what is called weakly complete finitely generated algebras. So if we have a K-algebra, smooth K-algebra, then we lift it and we complete it periodically. And then we consider a certain subalgebra which is weakly complete, which we denote by a dagger. In our example, so here A would be Kx and A bar would be Kx, A W Kx, and we already had the completion. And now we consider a dagger. Which can be described as follows. These are the series such that we have this condition there are different ways to describe this. Later we will see a different condition and we will, yeah. Sorry? The limit of the p order of the coefficients divided by n is greater than 0. And this gives us a good cohomology, rational one. So we will invert P and we will call the algebras dagger algebras. So this gives us a rational cohomology which is interesting enough, but also has good properties. For example, finiteness conditions. And is independent of lifts. Okay. So this was the affine case, and then this was further developed by Berthelot in terms of rigid cohomology. Which is in some sense a theory that unifies crystalline cohomology and Monsky-Weschnitzer cohomology in that it allows to treat proper but also open varieties over K.
sorry, maybe I don't understand what's going on, but in the conditions on the coefficients, like this excludes coefficients that are 0, no, up to a certain, that are eventually 0, no?
No, because infinity is positive.
Okay, sorry, thank you. My bad. Thank you.
So, as Alberto already told us, the rough idea is that, so the following picture. We start with k-varieties. We wanted to work with capital K-varieties, but this is not very good. So what we do is we try to regard them as formal schemes. Over WK, and then we associate to it a rigid variety over K. And we cannot do this in general on the level of varieties, but we can do this motivically. So this is natural in some sense, because if we recall that by work of Grothendieck, Elkick and Alamir, locally we can lift k-varieties, at least smooth k-varieties and their morphisms. Eta locally and uniquely up to homotopy. And this is built naturally in the framework of motifs. So it makes sense that we consider this in this context. So if we recall from yesterday, if we have a formal scheme, a smooth formal scheme S, we can consider its generic fiber and its special fiber. So S sigma will be its special fiber. And S eta its generic fiber. Then Alberto told us that we have the special fiber functor and the generic fiber functor induce functors on the level of motives. So in the middle we have formal schemes, formal motives. Then we have the generic fiber functor, which go to rigid motives. And on the other side we have algebraic motives. And Ayub showed that this is an equivalence. So maybe I will put this here because I will use these functors more often in this talk. Okay. But as we have seen before, if we also want to, so we want to obtain a cohomology functor, but we want that it has also good properties for open varieties. So we have to come back to Monsky-Weisschnitz's growth condition and build it in our theory of motives. And this brings us to Dagger motives. There are, as I said before, there are different ways to encode this growth condition, and we will take an approach that is in spirit closer to what Berthelot did. So if we have a rigid space, we want to endow it with a Dagger structure. Which I then denote by S Dagger. And this is given by a strict inclusion. And there's a representation in forms of a proadic space. Where the SH can be seen as strict neighborhoods of S inside of S0. So if we go back to our example, we consider X to be B1. So I denote this by A. It's not the same A because I have inverted P here. And we consider a bit bigger disk. And then we can consider XHs to be just disks in between. And we can see that the limit over these algebras here give us exactly the Dagger algebra from Onsky and Reschnitzer. So we have yeah. So if we denote this by AH, this is the limit of the AHs. Okay. And of course we have, we can write X, we have a sequence of neighborhoods of X inside X0. Now, by results of Bosch and Grosse-Klanne, we can always find such a Dagger structure locally. And they are unique up to homotopy.
You're speaking about smooth rigid spaces?
Sorry?
You're speaking about smooth affinoids or general affinoids?
Smooth. I mean, there's a way to do this more general, but it's sufficient for the moment for smooth. So this allows us to build the category of Dagger motifs, which I will denote by A Dagger, S Dagger, in the same way as rigid motifs. And Vezzani showed that there is an equivalence between Dagger motifs and rigid motifs. So now in our functor here, I can continue the sequence by adding Vezzani's equivalence. Dagger. So we land in Dagger motifs.
So Ayub's arrow is an equivalence or an isomorphism?
An equivalence.
Before you raise the boat is a collimate.
Yes. Yes.
Excuse me. Is there anything that can be said with weakly complete finitely generated algebra, like with motives or such, we could maybe consider complete the diagram using.
What do you mean?
We could also consider motives of weak formal schemes.
Yeah, but that's exactly what we do.
No, but like with the dagger thing.
In the middle.
I think it's, we also showed that they are equivalent.
Yeah.
Okay.
With
You meant here. Yeah. Sorry, I misunderstood. Yes, of course.
So it's equivalent still in the integral level.
Here, yes.
Okay.
Okay, so now we want to start to build our cohomology functor. So for this last category allows us to consider morphisms of Dagger spaces and the associated motifs. So we have something like X dagger over S dagger. And they are represented by diagrams of or morphisms of proadic spaces. So now we will consider a functor which I call VR dagger of X dagger over S dagger as the limit over the Ram cohomology. So here I take the solid, the Ram complex of XH over SH, and the limit. And to be precise, I have to consider Pushforwards. F is this morphism. And now we show that for that this gives us a functor from the category of Dagger motifs over S to the infinity category of solid quasi-coherent sheaves. So or more precisely, a Dagger version of this. And the Dagger version is just the limit over the solid quasi-coherent sheaves of for each SH. So now in our sequence of functors, we go further with this dr dagger to land in d dagger. No, this is eta dagger. Yes, sorry. Oh. And now this is very reminiscent of what Berthelot did. So let's consider this for a moment. Maybe I should write here. Okay. So what Berthelot did was he considered triples of the following form. So for a K variety S, he considered an open immersion. So we want to think of compactification, and then a closed immersion. So this is into a WK formal scheme. And we call this frames. And now we consider the tube of S and S bar inside this S. And this is a strict inclusion, so this gives us a dagger structure on the tube of S. Now, if we have a morphism of frames, then Berthelot made the following definition of the rigid push forward. So I denote this in this way. I mean, we want to think of a compactification, and it suffices to consider such, but one can consider all of them, or all anything of that type. So later we will look at realizations. So we want to consider all of the frames, which also are not, where the S bar is not necessarily proper, but they are included in the information. So it's sufficient to consider them.
And what do you mean by strict inclusion when you say that S is containing S bar is strict?
Here I'm thinking in the context of Huber's adic spaces, so that's in the sense of Huber.
The tube up, because the tube is always
Yeah.
is always in itself.
So we define this, Berthelot defined this as the push forward of J dagger of the Drame complex, now here I take the tube of the bars. So cherry dagger, just as a reminder, is
No. If you take the identity map and suppose S is a smooth affine and S bar is the same as S, and you lift it like before, so P is the lifting, then you don't. Then the tube is just the tube is just the rigid space of the general fiber, and the inclusion is the identity, and it is not. You don't get a dagger thing there.
Yeah. In that case, I just get convergent cohomology. But
okay. This is just notation. You don't say it's a dagger.
Yeah.
Okay.
So it's a bit subtle. So we really want to think about the compactification. If I have just the identity here, this will just give me always convergent cohomology.
Okay.
So the third line is not necessarily strict inclusion. Just sort of double inclusion. Is that the whole point?
Yeah, if I have the identity here, this is just, it's not a strict inclusion.
Okay.
Let's take a proper frame.
Yeah.
Oh.
So yeah. Yeah, we should really take here, so this is a subtlety, but we really should take here a compactification. And then we call this a proper frame. Yeah, so just as a reminder, the J dagger is the limit where V varies over all neighborhoods, all strict neighborhoods of S. In this case, x, the cube of x inside the cube of x bar. So this really gives, yeah, so this would be the J. So this limit is exactly what we see here also. So now the problem is here we looked always at cases when the whole morphism can be lifted. But now if S does not necessarily have a lift, so in that case, we just take all frames over S. So what we mean by this is we will consider the following category of what we call generalized frames over S. So these are triples of the following form. So T is a WK formal scheme. Then we have its generic fiber with a dagger structure, and there is a morphism from the special fiber to S. So now to our functor, what we do to our functor now is, okay, so how do I write this? I will write it here first, and then we will see that. So we go from S to dA of t sigma. And now we do the whole thing that we did before.
Performance goes smooth in this discussion?
Not necessarily. It suffices to consider smooth formal schemes. And now we apply our functor here and land in d dagger of theta dagger. And what we now do is we take, so this gives us a functor. And now we take the limit over all generalized frames over S. And we call this our Cohomology functor. Now, for this construction, we showed the following. If X to S is a smooth projective morphism of K varieties, then our rigid cohomology functor lands in the following category. The limit over generalized frames over S. And now vector bundles on theta dagger, and together with a Frobenius structure. And we call this the category of overconvergent F isocrystals.
So here vector bundle should be perfect complexes, or?
Sorry?
Because you're in the derived world, so it should be perfect complexes?
Yeah, perfect complexes, such that the cohomology groups are locally free.
No, the terms are local. The cohomology groups are local.
Yeah, perfect, yeah.
Okay. And the limit is like projective limit over...
No, because this is a huge category. It's a general limit.
So this category is not filtered or conflict, is a okay, this is considered as a classical category or as a higher category?
It's an infinity category.
You mean the frames is an infinity category?
No. This is an infinity category.
Okay. And then you take the limit of those things over this.
Yeah. And this is not the classical category, but it may, in view of this definition, it makes sense to call it F. So overconvergent F isocrystals.
But in particular, if you look at any given cohomological degree, is the claim that you get an overconvergent F isocrystal in the classical sense?
Exactly.
Okay, thank you.
Yes, and that's exactly what I wanted to say. So in that sense, it solves the following conjecture of Berthelot. Which was, of course, formulated in the classical context. So for a smooth and projective morphism, just like before, the family which is given by Berthelot's higher pushforwards for each n. Now formulated in terms of Berthelot's frames, comes from an overconvergent F isocrystal. And here I mean F isocrystal in the classical sense. And up to then this conjecture was shown only in some specific cases. So for example, Berthelot and announced a proof or proved it for if F is liftable. This was then written down in detail by Suzuki. Then there was a proof by Shiho in the case when it extends to a log-smooth morphism. Then there were some proofs for specific cases that in the end showed that August higher pushforwards come from an overconvergent F isocrystal. So that was due to Etes, Matsuda, Trion.
So in Shio, is it a proper log smooth morphism?
Yeah. You take nice compactifications. So if there exists a nice compactification of the morphism. And Ambrosi showed that August pushforwards come from an overconvergent F isocrystal. And then there were some versions in the crystalline world, in the convergent world, and also with coefficients in those contexts. By several other people. So in the last 3 minutes, I just want to...
Excuse me. So in his conjecture, did Berthelot define also the overconvergent F isocrystal, or he just said it comes from some overconvergent F?
I think he wrote it comes from an overconvergent F isocrystal, if I remember the formulation correctly. So, I mean, this basically means that you have an overconvergent F isocrystal and you realize it on a frame, and then, because an overconvergent F isocrystal basically is a family over all the frames. So in the last 3 minutes, I want to just give a sketch of the proof. So our X over S was smooth and projective, which means that the associated motive is in particular dualizable. And then our functor is symmetric monoidal, so this property of dualizability is preserved until the end. So we land in the dualizable objects of this category, but these are exactly the perfect complexes. And then we just have to show that the cohomology groups are locally free, but this can be checked locally for K. This can be checked for K points. And here we can see that the drum complex splits. And then we are done. Okay, I want to stop there. Thank you very much for your attention.
So I have some other question for the speaker.
What is the role of projective versus focal?
It's just technical. So it can also be shown for proper. Just for simplicity, yeah.
How about coefficients?
That's a good question. So we can treat motivic coefficients.
Yes.
But for more general coefficients, probably there's some other input needed than motives. Probably for the motives.
Thank you.
So this property of being symmetry monoidal, that's just like Kinet formula, or for the
It preserves the dualizability.
No, I know, but
Yeah.
what did you have to prove? You had to prove that it's symmetry monoidal, right?
No, that was already done by, I think, Vezzani.
Yes, it's the Kuhn formula.
Yeah.
And just in the last step of the sketch of proof there, so what is this principle about checking that the cohomology groups are locally free on k points?
That's because of the spreading out property.
Spreading out. But I mean, so if I interpret that completely naively, then to me it doesn't make sense because on k points the cohomology groups are obviously locally free. So, but I'm not asking for the proof. I'm just asking for the statement. Like, what is this criterion?
What do you?
Well, I mean, on k points, the cohomology is automatically locally free.
No, it's like around each k point.
So like the formal neighborhood.
Yes.
Yeah. Okay.
But then, because of the spreading out around each k point, the motive comes from the k point.
Right. There's this homotopy property. Yeah.
Right.
Okay. Understood. Thank you.
Yes. If I understand correctly, this takes value in isocrystals, so with P inverted. Can you also define some integral value community theory this way?
No, I mean, we use a lot of properties here that in the motives where we have to invert P. So maybe there's the work of, that's possible to do with the work of Kiertz and Tamme, who have some, so basically they show this using some version of Alabia's result, and they get some some way of to construct crystalline cohomology that way, so integrally. And then there's a student of Kiertz who does this for the Mons-Querschnitzer cohomology, but I don't know how far they are here, but probably they can, at least one can define a category of crystals.
Okay, so if there are no more speakers, let's thank Veronika again.